Now, I want to go over a couple of really basic things, algebraic things, because there's some disconnects. Yeah, some people nailed every problem. That's great. But I'm more concerned with people who made the same errors over and over again. Often we make the same error in every problem. So I'm going to ask you a really simple question. I have a function, let's say f of x equals x squared. You know, not really exciting, simple parabola. I want to evaluate at x equals 3. So notationally, how do I say this? Because in some cases, there's more than one correct way to say something. Now, we all know what the result is, but how do I express it? Sorry, I just erased it. At x equals 3. Well, the most formal way mathematically, and the way that you get used to as you go further in math, because this one always works, is we'd say f of x, vertical bar. This always works because sometimes, like in Calc 3, we're going to have multiple variables. Or sometimes we might evaluate something at an actual point in space. So this says evaluated at x equals 3. What's another way I could say it? The more slam dunk easy way? F of 3. That's what that means. And that would be 9. Do we all agree with that statement? F of x evaluated at 3 is 9. Tell me, what do you think about this statement right here?
It'll work.
It doesn't work.
Is this correct or is this incorrect, first of all?
Incorrect.
It's incorrect. Why?
Because it would just be a flat line of...
F of x equal 9 is that horizontal line. Let's say that's 3, 9. This is a function. This is the function evaluated at a scalar producing a scalar. The function is not equal to a scalar. This is one of the most egregious errors you can possibly make in math. This is probably the most common error we made on the quiz. We're taking a function and we're saying it's equal to a scalar. That means that this is a horizontal line and is no longer a parabola. No, f of 3 is 9, f of x isn't 9. This says f of x evaluated at x equals 3. This is shorthand notation, absolutely, write it this way. But there's a lot of times we're going to be doing things where the only way you can write it is to do the evaluated at. I just want you to get used to seeing that. Not a big deal, okay? So we've got that. Now, the next thing is when I'm writing a limit, oh, my black pens died last out at sea. Oh, maybe there's one here. When I'm doing a limit, let's do one we've done before. I have the limit as x goes to 2, let's say, of x squared minus 4 over, how about x plus 2? I want to do x minus 2. We know this is the indeterminate form 0 over 0. Don't write equals 0 over 0. Because that means 0 over 0 would be a value, and it's not. It's the form, and the way we usually write that is we say it approaches the form. The reason this part is so important, whether you write it or you see it in your head, it's so important because that dictates your strategy. What if my numerator was approaching 0, but my denominator was not? You know, what if that's x minus 3 on the bottom? What if my numerator is approaching 0 and my denominator is not? Then what's my limit? Just be 0. What if my denominator is approaching 0, but my numerator is not? We hated those. Are you pointing upwards? Oh, that was the right answer. That means I had a vertical asymptote. Oh, we didn't like those. Those were evil and icky, right? Infinities all over the place. If they're both approaching 0, that means I can probably factor and cancel. In other words, the form dictates the strategy, and it tells me, what if I have a situation where they're both approaching infinity? Right? We looked at that last day. So in this case, I would factor it, right? That's obviously x plus 2, x minus 2. So I want to say this is equal to the limit as x approaches 2 of x plus 2. Do we all agree with that statement? We've done this problem before. Now, here's what we're doing algebraically. You did this, even in remedial algebra, we did stuff like this. Is this statement absolutely true? We talked about this on day 1. Can I say this in absolute? Well, what's the domain on the left in words?
X n equal 2.
So all real numbers,
Except
except 2. What's the domain on the right? What's the illusion of the domain on the right? All real numbers. The one of the absolutes in mathematics, that this is an unchanging thing, is a domain cannot change. So I can't all of a sudden add a number to the domain. So what did we say? We say this is identically equal to this for all real numbers except 2, because I can't have a 2. So I call it the disclaimer. Are we okay with that? We did this, by the way, even in remedial algebra, you did stuff like this. You're saying these quantities are identically equal except here, because that's not a number. So when I write this limit, I'm saying this quantity is identically equal to this quantity at all real numbers except perhaps 2. Whenever you put an equality between limits, this is very important that we understand this about limits in general. When I say this is what we just did. I have a function, I did stuff, I manipulated algebraically to get hopefully a simpler function, and I'm putting an equality between them. We are saying that f of x is identically equal to g of x for all real numbers except perhaps that one. That's what we are absolutely saying 100% of the time. Here's where we're getting into trouble. What is this limit?
4.
Do we all agree the limit is 4?
Mm.
Tell me about this statement right here. Are you happy with that statement? What did I just say? I just said the quantity x plus 2 is identically equal to 4 for all real numbers except perhaps 2. X plus 2 is not equal to 4. X plus 2 is x plus 2. I just equated a function and a scalar. We have no problem from here to here because I simplified. This is not true algebraically. This is not true in any conceivable concept. I just made this line equal to the horizontal line y equal 4. Remember how f of x equals 9 you said was incorrect? That's the same mistake. I just evaluated the problem. This is the limit of my limit. I can't have a limit there. That's incorrect. When you take a limit, the moment whenever you write an equals after a limit, if it's still a limit, it means you're still doing algebra, you're still doing stuff. And most problems, you're probably doing a couple steps. Once I evaluate it, I'm now done. Do you put an equals after this? It wouldn't make any sense because it's 4. That's it. That's it. When I evaluate a limit, I drop the limit and I write 4. All right. Having said that, true or false?
False.
False. I just said the limit of that function is equal to this function. It is not. This is an egregious error. In fact, this is one of the biggest errors that can possibly be made. This is a scalar. I just set it equal to the original function. That doesn't make any sense mathematically. That's a bad error. Most of us were doing things like this. We put an equal sign. By the way, once I put equal and I drop the limit, as an absolute, you are done. There cannot be anything else. Would you find it silly if I said the answer was 4 and now 4 equals and I put another number? Would you say that's kind of ridiculous, bad math, terrible? If the answer is 4, we're done. Can you have the answer be a function for a limit question? Yeah, you had a couple of them in the first quiz that were. In fact, from this point on, all of our limit problems are going to end up as functions, not as scalars. That's okay. The moment I drop the limit and I write equals, that is the answer. That answer can't equal something else. So here's what a lot of us did. We said the limit of this quotient, which my final answer should be a scalar, we said is equal to this function. I can't go any further. I dropped the limit, I evaluated it. But now I'm saying this function is identically equal to 4, but that's only true if x is 2, and x equals 2 is not in the domain. I can't evaluate this at 2. And I'm not taking a limit anymore. So this isn't equal to this, and this is definitely never equal to this. We can't drop the limits prematurely, because once you drop a limit, that has to be your final step. There can't be another step after. So if I said f of 3 is 9, and 9 equals, you'd say, no, you're done. Once you evaluated it and got your 9, you're done. There's nothing else to write. A lot of us we're keep going. So this is an easy fix. If you're manipulating algebraically, you're saying this limit equals this limit because I'm not ready to evaluate. Why are we not evaluating this? Why are we not giving the answer right now? Because it's an indeterminate form. When I do, we'll put the limit back in here. Is this an indeterminate form? This, x plus 2. No. Therefore, now I can evaluate it. Now I'm done. That's how most limits work when they're friendly. Sometimes you have to do a little bit of work. Okay, but the moment you can evaluate the limit, you evaluate it, and then that's the end of the problem. But you don't write limit again. So there's two different things that was going on. It's an easy fix. A lot of us were writing, we did the limit correctly, and we wrote the final answer was the limit of our final answer. So we left the answer to this as the limit of 4. That's not true. It's just 4. Or we didn't do any limits anywhere in the problem, and we said the limit of the function equals the function, which equals the scalar, which is really bad. So we fixed it. Easy fix. Because today, we're actually going to use limits to do really, really huge, important, cool, crazy stuff. Okay? Now, I want to consider, let's consider a simple graph like f of x, I don't know, how about x squared? That's a really cool graph. I'll use blue, if there's anything left here. Now, let's consider the point 1, 1, which is right here. If I pick any other point on this curve, any point on this curve, okay, let's say, for example, I pick the point 2, 4. And then I consider the line passing through them. My best here. What is that orange line called? It actually has a name. Anybody know? Not yet, because it has 2 points on it. You're in the right realm, but not yet. It's called the secant line. Any line that passes through 2 points is called a secant line. Okay? So that's a really exciting line. It's a secant line. How do I find the slope of that line? Well, technically, if I said, what's the slope? Would you agree the slope would be f of 4 minus f of 1 over 4 minus 1? My numerator is the change in y, my denominator is the change in x. And what would those, I'm sorry, f of 2. My bad, I looked at the wrong number. Sorry. F of 2 minus f of 1 over 2 minus 1. And wouldn't that be 4 minus 1 over 1, which is 3? So the slope of that orange line is 3. Let's pick a point that's closer. What if I picked a point, let's say, I don't know, 1.1? And I'm going to be lazy and write 1.1 squared. But we'll calculate that in a moment. Now I want a different secant line. I want the secant line that passes through these 2 points. Well, hopefully you can see that line had probably a little less slope now, agreed? So the second line I want is now f of 1.1 minus f of 1 over 1.1 minus 1. Well, that would be 1.21 minus 1 over 0.1, and that's 2.1. Okay, so my next line has slope 2.1. Let's get closer. Let's get even closer to 1, 1. Let's just make it a small difference. How small is a small difference? Well, I'm going to show you how small it's. I'm going to blow that spot up. I'm going to make that way bigger, right there. I've got, here's my 1, 1. I'm super blowing it up, right? We've done this, right? I've had you back way out, we've blown way in on the Desmos, right? We've done all these things. Now, I'm going to pick a point so ridiculously close to that that you can't see it unless I blow it up. So I'm blowing it up, and now this point's going to be 1 plus delta x, and then the square of that. And I want delta x to be small. Delta x just simply means change of x, right? All right, that's close enough. All right. Now, I want to find this slope. I want to find this slope. Well, I'm not doing this, no calculus yet. I just want you to tell me it's m of what? F of 1 plus delta x minus f of 1 over 1 plus delta x minus 1. Well, so far, because it's y equal x squared, I'm just squaring that number. I'm squaring the 2. I'm squaring the 1.1. So what should I do to 1 plus delta x? Square it. Yeah. I'm going to square this thing. So if I square that, it's going to be 1 plus 2 times 1 times delta x plus the square of delta x minus 1 all over just delta x. Oh, the ones can cancel. So now I've got 2 delta x plus the square of delta x all over delta x. Does this reduce? I can factor the numerator and then cancel. That's 2 steps. I'm too lazy for that. I can multiply numerator and denominator by 1 over delta x. That's 1 step. Or I can do the easiest way of all. What will I get when I pull those apart?
2 plus delta.
2 plus delta x. Huh. Now let's think about that for a moment. Technically, isn't 2 1 plus 1? So in other words, my delta x would be a 1 here. Do you agree? And what's my slope? 2 plus 1. In the second problem, my delta x would be a 0.1. And what did my slope end up being? Oh, 2 plus 0.1. You said something about a tangent line. Problem with trying to measure tangent line, it's only 1 point. What if? What if I had delta x get smaller and smaller and smaller and smaller, so these points got closer and closer and closer and closer together? You're going to get used to the smell. It smells like a limit. So when I say, what does it smell like? You're going, oh yeah, clearly that smells like a limit. A limit of what though? What do I want to do with delta x? Have it approach
1.
1? Do I want delta x to approach 1?
2
Approach 0. Yeah, I want to make that distance between them smaller and smaller and smaller. I can't make it equal 0, but I can make it approach 0. Why can't I make it equal to 0? It's in the denominator. But can I have it approach 0? Can I have it approach 0? Yes. So if I took the limit as delta x approaches 0, let's go back to this. Of f of 1 plus delta x minus f of 1. That's what we just did. And now it's delta x because we saw it canceled. We know it's the limit of this. We just did that. So that's the limit as delta x goes to 0 of 2 plus delta x. I cannot replace delta x with 0. Because essentially what that means, I'm dealing with 1 point. So my numerator would be a 0, my denominator would be a 0. But I said consider delta x as being something really small, and we just calculated the slope to be exactly this. Now if I say let's make those points get closer and closer and closer and closer together, what am I describing then? I'm describing the tangent line, aren't I? I'm describing the one line that passes through 1, 1. Would it be safe to say that this equals the slope of the tangent line? Do you think that would be safe to say that? Yeah, because that's exactly what it would be. And what would it be exactly? You can evaluate this. I can't evaluate this, but after I did some algebra, I can evaluate this, and this would just be
2.
2. And that seems reasonable. If it helps, we used 0.1, now use 0.01, now use 0.00000001, and every time you do it, your slope's going to get closer and closer and closer to 2. The slope of the tangent line can only be gotten via a limit, because I'm only using the 1 point. Now, how many have ever had physics? High school physics even. I remember physics. It used to drive me crazy. Okay. All right, you got the ramp, and you got your little Pinewood Derby from when you were in your Cub Scouts or whatever, and I want you to have it roll down the ramp, and I want you to calculate the velocity maybe every 1/10 of a second. Remember doing stuff like that? So you got to do like 100 calculations. I got to start over each time and do a new calculation. Wouldn't it be easier if I had a simple formula that I could just substitute the different times into and then calculate? Wouldn't that be like way better than to go from beginning to end to get one value and do the entire process again, second value? Oh, I forgot to tell you. We just did all of this work to find the slope of the tangent line at 1, 1. But I have a list of 237 other points. So we got to do this 237 times from beginning to end. Are you happy with that? What if we did this problem, instead of at a particular value, we just did it for any value of x? And then in the end, I could replace x with, in this case, 1. And then the next problem, 2. And the next problem, -3. Wouldn't that be more efficient if I did it that way? Yeah, and that's, by the way, pretty much how we're always going to do things from now on. So now let me go back to here. And instead of 1, 1, no, way cooler than 1, 1. I've got a point, how about x comma f of x? That's my starting point. Now, I want another point on the graph. Let's call it, I don't know, x plus delta x comma f of x plus delta x. Now, in this example, my x was a 1, so f of 1 was a 1, and then we did the exact same thing. But I want every point on the graph to be able to be represented here. It'll make my life so much easier if I could do this leaving the variable in there. When you learned your quadratic formula back in baby algebra, right, you had a quadratic of the form ax squared plus bx plus c equals 0, and then you learned the formula ABC. And I taught high school algebra, and they said, well, why do we have to do it with variables? Why can't we do it with numbers? Because then you'll only be able to solve the quadratic formula for that one equation with that one set of numbers. You learned it with the a, b, and the c, so you knew where to put the numbers in, no matter what the quadratic looked like. Infinitely superior way of learning it. But it's always kind of scary at first when we're using variables instead of numbers. But when I'm using variables, then I'm going to get an answer that's true no matter what numbers I use. Way better. I'm going to get something in a formula rather than just get a numerical answer at the end. Because a numerical answer in the end is not going to help me if I don't know how to get it for the next problem. So let's find the slope between these two lines, and we'll call that m of the secant line. I actually want, where did I do it in orange? I want to take this secant line right here. I want to find that slope. No limits, no calculus, just that slope. Do you agree that it would be f of x plus delta x minus f of x over x plus delta x minus x, which would just be delta x? You agree with that? Yeah? Okay. Now, what is f of x plus delta x? If I replace x with x plus delta x, then that means I'm going to square the quantity x plus delta x. That was x squared. Okay. Let's go ahead and square that. I mean, we did it a moment ago with a 1 instead of an x. So that would be x squared plus 2x delta x plus the square of delta x minus x squared all over delta x. And I think I can cancel those guys. So now I've got it down to this. Hopefully this looks kind of familiar with the exact same places we were here with a number. But here's the beauty. That was only true when x was 1. This is going to be true for every real number x. So this is way better. Now, can I break this one up like I did the other one? Yeah, I mean, I don't care how you do it, but whatever we get, we want it to be correct. If I pull this apart, what am I going to get? Listen,
2x
2x,
plus delta x.
just a delta x. Now, in the last example, I used an x value of 1. It's right here, isn't it? Is that 2x plus delta x? Yeah, I just didn't realize it was an x there. We did all this to get this answer, but we were done. We couldn't use this result for anything else. Now, this is the slope of the secant line for any other point on the curve. I want the slope of the tangent line. What's the difference? It's going to be the limit. As delta x approaches 0 of f of x plus delta x minus f of x all over to delta x. It's kind of sloppy. Now let's take the result. I'm not going to redo the problem. Let's just fast forward to here. Won't that be the limit then as delta x approaches 0 of the quantity 2x plus delta x? And what will that be? I can evaluate this because it is no longer a quotient. That's really the key. So what is this value? If delta x is approaching 0, what am I left with? Delta x is approaching 0. 2x. X isn't doing anything. Delta x is approaching 0. This is 2x, which absolutely agrees with what we got on the other one. But here's what's cool about that. I would like the slope of the tangent line. How about just for fun? Here's the point 3, 9. Can you tell me the slope of the tangent line right here? Yeah, what is it? 6, 2 times 3. How about at the origin? Tell me in words about my tangent line at the origin. Shouldn't it be horizontal? Do you agree that at the origin my tangent line should be horizontal? Because it's going uphill and it's going downhill. But at 0, 0, that means my slope is 0. How about if I go to negative 2, 4? Well, we know parabolas are symmetric. They look like a mirror image. So at 2, 4, my slope should be a positive 4. So how about at negative 2, 4?
Negative 4.
Do you see the consistency now? It's like, that's beautiful. This is infinitely superior to come up with something that's a function rather than a scalar. So I can now tell you the slope of the tangent line at every point on the curve. Beautiful. So we give this a name. This is called the derivative. And in fact, we're going to go a step further. The very, 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 very first application of derivative is graphing, and particularly slope of the tangent line. But we're going to see derivatives go way beyond this. We have uses that are way beyond graphing. Way, it's not even close. So I'm going to give you a simple analogy. You're driving your car. Let's say you're on a long trip. You're driving your car. Are you going to drive a constant speed the whole duration of the trip? No. No, that seems kind of silly because you're going to be stopping, you're going to be going. So let me draw you a simple picture of your trip. You left home. You're speeding up and then you're slowing down, you're stopping. Now, one of the things that a lot of people don't realize about graphs, think baby algebra, think XY stuff that you did in algebra. We just did this, talked about this in Calc 3 today. How many have had any form of physics in your life? High school physics, probably. One thing you learn is there's no such thing as a unitless graph. That doesn't actually make any sense. Absolutely every graph you ever drew in your whole life, every one you ever looked at, had to have units. It's just in math class we kind of ignore them. So we always draw unitless graphs. But the x-axis has to represent something. The y-axis has to represent something. What is slope? Now, I want to keep this simple. What is the difference between slope, or let me back up. First of all, what is slope? It's the change in y over change in x. So whatever units I have here, which in this case would be distance, divided by whatever units I have here, which in this case would be time. So slope would therefore be what?
Distance over time.
Distance over time, which is speed. Oh, the slope of my graph would be speed. By the way, this is like 8th grade math. I'm not joking. You're supposed to learn this as kids. Did you learn it that way? You probably didn't throw the units in, which puts you behind when you get to physics, that everything has units in physics, and you're saying, I've never done a graph with units, which is unfortunate because all graphs actually should have had units. Then slope is simply the ratio of that unit to that unit. Now, the word ratio, okay, in rate really mean the same thing. So when you go to the store today and you're buying your fruit, it might be measured in dollars per pound. When you get gas today, it might be dollars per gallon. When you're driving today, it might be miles per hour. These are all rates. Do you agree? What's the difference between a rate and a percent? You have a 100-mile trip and you drove 80 miles. So you say you drove 80% of your trip. Would that be a correct statement? Why did we say that? Because you drove 80 miles per mile. But if I drove 80 miles in 1 hour, we'd say we drove 80 miles per hour. The difference between a rate and a percent, there is no difference. A rate is two different units, a percent is the same units. Therefore, the units cancel. So when you're giving a percent answer, it means your numerator and denominator have the same units. Like 80 miles of my 100-mile trip. Does that make sense? I got 80 points on a 100-point test. But I drove 80 miles in 1 hour. Now I'd say miles per hour. Nobody says miles per miles, they just say percent. So every graph you've ever done probably had rates, but it could have been percentages because your units could have been the same. No big deal. But we get used to that. So in my picture here, if I draw any line segment and I ask you for the slope, so I'm going to do a simple one. What would the slope represent? The slope of the orange. This was, I started, I stopped. Average speed, perfect answer. Why? Because you just said, I went this far in this amount of time. I just drove 200 miles in 4 hours. My average speed was 50 miles per hour. Does that mean you drove 50 miles per hour the entire time? Right there, I have a slope. I'm going to draw a tangent line right there. What does the slope of this tangent line represent? It's how fast I was going
At that point.
exactly at that time. It's called the instantaneous rate of change. So a derivative, our first use of a derivative is slope of a tangent line. Actually, I want you to immediately go one step further. It's the instantaneous rate of change of the y to the x on my graph, because in real life when you go outside there's no graph. But we use derivatives all the time. The derivative, if I'm moving, it's how fast was I going exactly at that moment in time. Would you say you're going, let's just say this was 50 miles per hour is my average speed. Would you say you're going faster or slower right there? Much faster because it's a steeper slope. How about right here? Faster or slower?
Slower.
And at the beginning, technically, I'd have a horizontal tangent when I haven't left yet because I'm not moving. I should probably have a horizontal tangent at the top because I stopped. So the slope of the tangent line in this example is exactly how fast are you going at that moment in time. Does that make it easier to understand? That's what the derivative measures. The derivative measures exactly at that moment. We started the problem by finding the slope of the secant line, which is exactly the same as saying the average rate of change. From point A to point B, I want to measure the slope of that line. That's average. But right there, point A, right when you pass that landmark, how fast were you going? That's instantaneous. I'm not doing it over a period of time, I'm doing it right at that moment in time. Okay, so that's the way I want you to think of derivative. Now, in this case, we got this. So, first thing I'm going to do is go over notation. Derivative, when you're first doing calculus, is the ugliest notation there is. Everybody gets confused, and we write things, you know, your teachers are usually very forgiving for a while because everybody has trouble with the notation. But if we were in baby algebra, and let's say we're learning square roots, if I don't use the square root symbol correctly in the right place, no one's going to interpret my meaning, are they? Like if I put the cube root when I meant square root, or if I put the root in the wrong place. But we understand that a root, square root is an operator. So the first thing I'm going to talk about is operators. And this you've never heard perhaps, but it's really important. Can you tell me what each of these equals? Square root, natural log, cosine, limit as x goes to 3. What does each one of these equal? Anybody? You don't know? Wait, why don't you know what the square root equals? Well, you should be saying square root of what? Oh, all of them are missing the argument. We talked about that. These are all operators. Yes, some of them are functions, but they're all operators. You can only do an operator on something. I need to put something in here. I need something here. I need something here. A lot of people, I got a lot of these on the quiz, and this equals 10. I'm a math guy. I've helped author multiple books. I don't even know what the suggestion of this, the limit of what equals 10. I might as well put the square root symbol equals 10. No, I actually have to have a function here. You have the limit of nothing, the cosine of nothing. No, I have to have an argument. Oh, so the derivative, I'm going to show you what the differential operator is. And this is, again, back in the day when Professor Newton was first, perfecting this stuff and was getting ready to present it to the world, they didn't invite me. I think I was only a freshman at the time. They didn't invite me to the World Math Council where they were coming up with the terrible notation. And we do use terrible notation all the time in mathematics. The differential operator looks like this, d, and we actually say it like this, d dx. This is one symbol. This is not a quotient. You treat this like a square root symbol. It is one symbol. So right off the bat, that's confusing, isn't it? The little d means you're taking the derivative. The x means you're taking it with respect to the x variable, which is automatically your independent variable. Because I could put any symbol here, and then that changes the instruction. And you're going to learn all that in this class. Then when you get to calculus 3, where you have multiple independent variables, we change the notation slightly. But right now, that's one symbol. So in the last problem where I had f of x equals, I have f of x, let's see, write it this way, y equals f of x equals x squared. There's several ways I could ask this question, and I want you to get used to all of them because you're going to see all of them. And when it comes to notation, it's almost like English language when you have words that are synonyms, means the same thing. It doesn't matter which one you use, does it? Anybody reading it's going to come to the same conclusion. You can't always use the same symbolic notation for one simple reason. We sometimes write our functions y equals x squared. We sometimes write our functions f of x equals x squared. And the notation we use is automatically different, which is, again, confusing. So I want to take the derivative. So I'm going to say d dx of y, and then we write that like this. dy dx means I'm taking the derivative of y. I just go ahead and throw the y in the quotient. This is now the derivative. This is the instruction. So if I wrote square root symbol and now you want to put a 16, the instruction was take the square root of 16. What are you going to write? Equals 4. 4 is the result of you taking the square root. dy dx is the result of you taking the derivative, and in this problem it would be 2x, wouldn't it? This is a function. d dx doesn't equal anything. d dx is the instruction. Just like empty square root symbol is the instruction, I have to now apply it to something. What if I'm using f of x? If you're using f of x, there's no y in the problem. So what if I wrote it d dx of f of x? Most people love this notation best. We write it like this. And we read that f prime of x. Whenever you see this notation in this context, it means derivative. A lot of people like that notation just because it's easier to write. But it is limited. It does have some limitations. This takes longer to write sometimes. I am saying exactly the same thing. And again, it's equal to 2x. There's one more way. I just gave you a sheet of functions. I gave you cos x, I gave you x squared, I gave you a natural log of x, I gave you x to the 5th power. I didn't say y equals, I didn't say f of x equals, I just said, here's x squared. I want you to take the derivative. How do I do that? Then I'd say do d dx, and do it on x squared. And what would my answer be?
2x.
Once again. Am I saying the same thing in each case? Yeah, but I'm asking the question slightly differently, but I'm still asking you to differentiate the function x squared. Whether it was y equals x squared, whether it was f of x equals x squared, or it was just x squared. And in each case, that's the notation. Now, at first it's confusing because some of the symbols look so similar. Okay? So you with me so far? Again, that's the symbolic notation. So a lot of times the instructions will be, here's a whole bunch of functions. We're going to get good at this. Here's a whole bunch of functions. I want you to find the derivative of each one. And every one of them I'm going to call y equals. So all of your answers will be dy dx equals. Another page might be all of your functions are written as f of x equals. So your answers will all be f prime of x equals. And that's pretty much the only two ways you're going to see things over and over. But understand they're saying the same thing. So why do we use two different notations? Because we define functions this way and we define functions this way. What if my independent variable isn't an x? What if it's something else? What does anybody know when, by the time you get to physics and above, does anybody know what the only independent variable usually you ever use again is? Pretty much in every problem? Time. And you never use an x, you use a t. So when you get to physics, you're never going to use an x again as your independent variable. You're going to use time, because that's what you're always measuring. Time is the variable. And what's even worse is, that means the horizontal axis is time. Do you know what you always use as the vertical axis? X. Same thing, differential equations. Does it matter what letter of the alphabet I'm using then? No, it only matters, I need to know what the independent variable is, because that's what my answer is going to look like. I could have just as easily used a different letter. I could have used T's, could have used Q's. Doesn't change anything. The only thing I need is I need that to match that. Is it possible that these could be different? Yeah, we're going to be doing that in a couple weeks when we get to compositions of functions. Yeah, they can be different, then the rules change slightly. So we start with this. Do you suppose I could take the derivative of the derivative?
Yeah.
Just in general? If the derivative is a function, then it's like starting a brand new problem with a new function. Could I take the derivative of that? Yeah, we're going to give that a lot of physical meaning. My Calc 3 class today just learned something. How many have ever done vectors? We talk about vector. We describe motion in 3 dimensions now using vectors. The first derivative is the velocity vector. And the derivative of that?
Acceleration.
It's the acceleration vector. Really cool. So if my first derivative measured the instantaneous rate of slope on the picture I just drew,
That's the rate of change of the slope.
then the rate of change of the slope would be the acceleration. Oh, so second derivative actually has meaning. And in this class, you're going to do just as many second derivatives as you are first. And most of the time, the second one's easier, most of the time, because you're dealing with something smaller than you started. Question is, how do I write that? I want to do d dx of d dx of y. Well, first of all, we said this is essentially d dx of dy dx. You are not multiplying. This is the operator. When you write cosine of something, you put parentheses. When you write square root on your calculator, you put parentheses. We put parentheses so we know what it is we're working with. So the way we write this is, and if that ain't confusing, I don't know what is. This looks really crazy, doesn't it? Now, the y still is a y. Y is my dependent variable. It's my function. It's the thing I'm taking the derivatives of. This seems redundant. The 2 means it's the second derivative. You can do it twice. Does it feel redundant that I'm putting a 2 on the bottom as well? Yeah, it seems kind of repetitious. This means I'm taking 2 derivatives. This means both derivatives are with respect to x. As if they could be something else. When you get to Calc 3, it's always something else. In Calc 3, you have multiple variables. Oh, so I could have 2 derivatives on top, but an x and a y on the bottom. I could have 5 derivatives on top, a couple of them were x, a couple were y, one was z. It gets crazy. It's cool, but it gets crazy. For Calc 1 and Calc 2, you're only dealing with one independent variable. These will always be the same for 2 semesters. Then what we do is we expand into 3D. It doesn't get weird if we just open it up and we can do more. But we still hold on to the notation we're learning. The one thing I like to do is give you the notation. Unfortunately, a lot of textbooks are really bad at this. They'll give you a version that works okay for now, and then when you get to Calc 3, they'll say, okay, remember all that notation we did? Scrap it. You can't ever use it again because it doesn't have any analogy in 3D. There are really bad notations that are sometimes used. No. Everything we do in this class will have a natural extension in Calc 3, and the tweakage is minimal. Minimal tweakage. So this is how you say second derivative. So what if I wanted the 10th derivative? You know, I had a lot of time on my hands. You know, I was bored. You know, the internet was out. I just wanted to take derivatives all day long. How would I say the 10th derivative? Tens. Oh, okay. They got a match. Now, the F notation. You're never going to get this one in a million years. You want to try?
Double prime.
Yeah.
You saw the movie. Now, I said this notation is very limited. I want you to do the 10th derivative here. I write a 10. I want you to do the 10th derivative here. I want you to do the 25th derivative, the 137th derivative. When I get my water bill every month, I get my number on top. It's one or two numbers, and then there's a whole bunch of zeros in a row. And I do the same thing every time with my pen.
Absurd zero.
I put little dots on all the zeros as I'm counting them, because I got to put that number on my check. There's a lot of zeros. I don't 5 or 6 zeros, and it's really very small. If I leave one zero out, it might be a different serial number, and I'm paying someone else's bill. I got to get it right. You really want to count the slashes? No. So here's the rule of thumb. We're okay up to third derivative. After 3, we write it like that. We're lazy. And this has something that's a very cool thing. It has to do with your brain. And I have fun with this one because I learned this as a kid and I didn't believe it at first, and then I've seen the experience a million times over. Most people cannot picture 4 things. You're exceptional if you can picture 4. And if I say close your eyes, let me give you a simple. Picture a circle. Just picture a circle in your head. That's easy. Now picture a circle and a square. Okay, I can do that. Now picture a circle and a square and a triangle. By the way, most humans now are very challenged. Very few human beings now picture a circle, a square, a triangle, and a question mark. Most people can't do that. You can't picture all of them. And if I kept going, forget it, it's done. And we have evidence of this throughout human history. Let's start something simple like dice. What's the most number on any die? 6. And how do we represent it? We do 1, we do 2, we do 3, we do 4, we do 5, we do 6. You never have more than 3 in a row. Roman numerals. What's the most number of symbols you ever have in Roman numerals? 3. Because the number 4 is 1V. The number 10, right? 8 is V111, or I, whatever you want to call it. But 9 is what? 1X. So in Roman numerals, you never have more than 3 symbols in a row. Your phone number. So if I said, what's your phone number? It's 592, pause, 8638. And of course, when you're dialing the phone number, you must pause, right? Or do you have to pause? Why is your phone number, your 7-digit number, why did it break it up like that? Because if I gave you 7 digits, you'd never remember. Your social security number is how many numbers? 9. And how is it broken up? 3, 2, 4. Why isn't it one big sequence of 9? Because you'd never remember it. Why isn't it 3, 3, 3? Because if all the sequences were 3, what might you do? So by going 3, 2, 4, it's easier to remember. You can go on and on and on. People have a hard time learning and relating. When I'm doing derivatives in this notation, I just put the number. It's easy. When I'm doing derivatives using prime notation, I use slashes only up to third derivative. In this class, you're never going to take a third derivative. In Calc 2, you're going to take a lot of derivatives because you have to take enough derivatives to see a general pattern of something. That might sometimes be 4, 5, 6 derivatives. So sometimes it's necessary to take more. For most things, you're never going to do more than 2, but you will often do 2. If you're doing 1, you're probably doing 2 usually. That's how it kind of works. Okay? You with me so far? So far, so good? Now, I'm going to give you a little bit of an algebra review because we need this to do the next thing. We're going to derive a humongous formula in a moment. We have something called the binomial formula. And we use this, oh my gosh, we use this in so many places in mathematics. Huge in statistics, it's huge in algebra, it's huge in Calc 1 and in Calc 2, it's huge in differential equations. I don't use it in Calc 3 or linear algebra. And it's huge it's probably biggest in discrete math. It's this one here. We can go on and on and on and on and on. Some of you remember doing this, and the trick was to figure out the coefficients. It involves something called a combination, things involving factorials. So my goal eventually was to get something that looked like this, a plus b to the nth power for any positive integer n. But if you remember, if I drew the picture of just the coefficients, does this look familiar? This goes forever. What's this called?
Pascal's triangle.
Pascal's triangle. And there's actually something called Pascal's formula that helps you do the computations at any row. Can anybody tell me the next row without doing any work? Okay, I'm going to give you that one. Oh, heck, I'll give you that one too.
4, 6, 4.
In fact, I'm going to go ahead and give you that one, and I'm going to give you that one, and what goes here?
6.
Because it's always the sum of the two guys. So some of you remember this. So here's the problem with using this. I want you to do a plus b to the 27th power. So does that mean I need to do all of the rows? In other words, I need to know the row. No, there's got to be a better way than that. Do you agree there's got to be a better way than that? Yeah. Well, in each case, here's what I do know. Absolutely, I know this is going to be an a to the n. What's going to be the next thing? It's a to the n minus 1b, and that's an n. And I know how it ends, too. It's all the guys in between that I have to remember. So I'm going to remind you of something, and this is only to produce the next formula. We are not going to use this again in this course. But I need you to see this so you know where the next stuff comes from. Okay? The next stuff comes from what's called a combination. Now, how many remember that's n? So I had to do that. I have to do that. That's called a what? What does the exclamation point mean? Factorial. Okay, what is n factorial? That's n times n minus 1 times n minus 2 all the way down to 1. So first of all, the factorial is only defined for positive integers. Okay, positive integers, that means 1, 2, 3, 4, 5, on and on and on. So if I said, what's 5 factorial? Well, that's 5 times 4, 3, 2, 1. What's 1 factorial? That's just 1. Now, it turns out, and again, I do this in differential equations. We derive something that's called the gamma function, and this is a special case of that. You can actually calculate 0 factorial. Somebody do this on the calculator, please. The factorial key is the one with the exclamation point. So everybody has one. It should be a main key, really. If you calculate 0 factorial, what does it come out to be?
1.
Yeah, strangely enough, it's not 0. These don't end at 0, they end at 1. See, if these ended at 0, then all factorials would be 0. Well, it'd be easier, but it'd be kind of useless, wouldn't it? So this is a special case. There's no negative number factorial. There's no fraction factorial or decimal factorial. This is calculated to be 1. And again, it's something that you're going to learn in a few semesters. So why am I showing you that? Because combinations, which are where these coefficients come from, if I said I have n distinct objects, and I want you to choose r of them, r being less than or equal to n. Okay, I have 50 people in the room, and I'm going to take 5 of you with me to lunch tomorrow. If you're one of the 5, does it matter if you're first, second, third, fourth, or fifth? No. I have 5 people, I want to form a basketball team. There's no order. I'm just grabbing 5 of you at once. This is called a combination. This is called a combination, and the number of ways of doing this we say is n choose r, and we use this notation. How many have had statistics? So you spent a lot of time on these, I would hope. In pre-calculus and intermediate algebra, you were supposed to spend time on it. Hopefully you did. And that's pretty much it. You're going to do these a lot in Calc 2, a lot in differential equations, and in discrete math, because they're useful. But what is this? I have 50 of you. I want to take 5 of you with me to lunch. It's n factorial over n minus r factorial, r factorial. Okay? If I said I want to take, there's 50 of you, I want to take all 50 of you with me to lunch. How many ways can I do that? 1, and that's to take all 50 of you. There's 50 of you, and I don't want to take 5 of you with me to lunch. I'm in a bad mood. I want to pick the 45 I'm leaving behind. Is it the same value? 50 choose 45 the same as 50 choose 5? Yeah, because the denominator. So picking 5 of you is equivalent to leaving 45 of you behind. They still have a 5 and a 45 in the denominator. I decided I don't have any money, so I'm not going to take any of you with me to lunch tomorrow. How many ways can I do that? One way. But both taking all of you and taking none of you has a 0 factorial in the bottom, doesn't it? Think about that. I'd have 50 factorial on top, I'd have 50 factorial and 0 factorial on the bottom. When you told me the answer had to be 1, that means 0 factorial has to be 1. That's another way of seeing that. I need this in this calculation. Why? Because this is n choose 0, which is 1. This is n choose 1, which is n. So the next one is n choose 2. This is the 4th row. So in terms of, by the way, you all have a key on your calculator that does this. This is 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4. If I'm using the combination key. It's the one with the big C and little n and r. It's very convenient. You don't do the factorials. You use the key on your calculator. It's way faster. But that tells me what each coefficient is as I go all the way to the end. And that's the part I needed, was the coefficients. Okay? Here's why I'm going to do that. Oops. We're going to derive the first and actually one of the most important derivative formulas there is. Okay, give me a little notation. That means element of, that symbol. Does anybody know what z plus is?
Positive integer.
Good. Capital Z is the positive integers, z plus is, excuse me, capital Z is the integer, z plus is the positive. What if I said z minus? What if I said z? All. I'm telling you n is a positive integer. That's the same, by the way. Most of the math books will also write it this way. What does capital N represent? Does anyone know? It's a word that starts with N. Natural numbers. The natural numbers are the positive integers. 1, 2, 3, 4, 5. Okay, that's one of your number sets. The natural numbers, a lot of textbooks will use the natural numbers. I like using Z plus because you use Z in so many different ways in all of your upper level math classes that you're going to be far more used to seeing that symbol. N you don't see as often. You might say, well, what's N again? But if I understand the big Z. Okay, so for n being a positive integer, here's what I'd like to do. I would like to take the derivative of x to the nth power. Now, we just did a problem where n was 2. I want to do this for every positive integer n. And if it makes this easier, think of n as being really, really large. Make n be huge. Make it so that the algebra would be horrific. You know, n could be a bazillion. Yeah, bazillion is the largest number there is. It's like 1 short of infinity. It's so big. It's my favorite. N is a big exponent. So this is not just x squared. This is x to the really big exponent. And the only way I can do this is with limits. So this is the limit. You're going to like this. This is kind of cool. As delta x goes to 0 of, f of x plus delta x is just this. So x plus delta x to the nth power minus x to the nth. Right? That's the formula we just created. That's f of x plus delta x, f of x. Now I said, imagine n is large. It means I got to expand this. Is that a big yikes? Yeah, but I got a big room. I might have to go around a couple times, you know, because I got to do this. So let's do the best we can with this horrific thing. So let's go ahead and do the first one. You'll like this. Okay, it's going to be x to the n plus n x to the n minus 1 delta x to the first power plus n choose 2 x to the n minus 2 times the square of delta x. How many times got to do this? N more times. Plus bunch of stuff with delta x cubed or higher. True or false? What's the next term going to have? Delta x cubed. What's the next term going to have? Delta x fourth, fifth, sixth, seventh, eighth, all the way up to n. I said imagine n is large. there's a lot of terms that I'm leaving out. But everyone sees what the next term and the next term and the next term and so on? All right. That's this. Minus x to the n all over delta x. Boy, does anything cancel? Here's the cool thing about the definition of the derivative, which is what this is. The limit is of f of x plus delta x minus f of x over delta x as delta x goes to 0. That's called the definition of the derivative. If I do it right, in most cases, the original function, which in this case was x to the n, is going to cancel. Why is that important? Because every single term left has at least one delta x in it. Is that important? Yes, because I have a delta x in the denominator. If I have even one term in the numerator that does not have a delta x, then this is a DNE. It's impossible because I can't cancel. If I do it right, then every term that did not have a delta x in it is going to cancel. So what does that leave me with? Well, that leaves me with delta x goes to 0 of n x to the n minus 1 delta x plus n choose 2 n minus 2 delta x squared plus a bunch of stuff delta x cubed or higher. Okay. All over delta x. Every single term has a delta x in it now, at least one. Agreed? Can I factor and cancel the delta x's, or can I just break this up? Be lazy. What's the next thing I'm going to write? I'm going to cancel a delta x from every term. So what's left? N x to the n minus 1 plus n choose 2 x to the n minus 2 times a single delta x, correct? Agreed? One delta x. Plus bunch of stuff, delta x.
Cubed.
Cubed?
What's squared is
How about squared or higher? Okay. There's no quotient. Can I evaluate this limit now?
Mm-hmm.
Tell me about a bunch of stuff.
We're all going
Oh,
to
that's going to 0.
multiply by 0. So
What about this term?
join to 0.
What am I left with?
And next to the n minus 1.
Oh, you've got to be joking. That's it? Yeah.
Mhm.
It's one of the most important formulas in all of calculus. The derivative, for n being a positive integer, the derivative of x to the n is simply n x to the n minus 1. Is that cool or what?
Mhm.
Yeah, that's very, very cool. That is very, very cool. That's the first calculus formula. It's far from the only calculus formula. So hold on a minute, let me see. Make sure how many calculus formulas we're gonna go today. We're gonna do a lot. Okay, this is just one of them. Now there's a whole bunch of more things we're gonna do. The two most important limit formulas, or limit properties I should say, the ones that apply to other areas in mathematics. We have the limit of the sum being the sum of the limits. We have the limit of the scalar multiple being the scalar multiple of the limits. Then we had limit of the product, limit of the quotient, and even, I was doing this in Calc 3 to remind them, limit of the composition is the composition of the limits. Those three do not extend to anything else in mathematics, but the sum and scalar multiple do. So the next thing we're going to do is derive the derivative of a sum and the derivative of a scalar multiple. We're going to derive those using limits, and those are incredibly powerful, and they're really easy. And then we're going to do a few more. Over the next few weeks, we're going to figure out how to take the derivative of every function, that exists. We're going to have well over 20 formulas in all. Yikes. So on your syllabus, you guys saw that sheet of formulas? Well, I have a sheet of formulas in every class that has all the calculus formulas eventually. All right? So go ahead and stop that. I'm going to do the roll.
There you go.
Okay. We would like to differentiate the sum of two functions. The only thing we're going to assume is that we know how to differentiate each one individually. So f of x might be a polynomial, g of x might be something else. I want to differentiate their sum. Oof. Well, first of all, using the definition of the derivative, this is f of minus parentheses, think of it like this. Now stare at that for a moment. Do you agree with that? If it makes it easier, think of it this way. Think of f of x plus g of x. Just call it a new function. How about h of x? So that's clearly h of x right there. So then if I said, what's h of x plus delta x? It'd be each one of these individually, wouldn't it? So that's what we have on the left side. Wow, this looks so big. Let me ask you, if I have a plus b minus c plus d, could I write that as a minus c plus b minus d? Could I do that? If I just wanted to start throwing things around. Would that be legal to do that? If I have that, could I do this? Stare at that one. Are these the same thing? If I distribute the negative, then it's minus c minus d. So put the minus c minus d. Yeah, no, maybe? Yeah, how many thumbs up do I have? Any? Couple sideways? Any downs? Yeah, it's true. Just make sure you believe it. Let's do that with the numerator. Can I manipulate the numerator, pull them apart? Yeah, absolutely. So I now have f of x plus delta x minus f of x plus g of x plus delta x minus g of x all over delta x. Isn't the limit of the sum of the limits? If I have a plus b over c, can I make that a over c plus b over c every time? Yes, no? Is that always true, what I just wrote? So let's do that. So this is now the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x plus the limit as delta x goes to 0 of g of x plus delta x minus g of x all over delta x. Okay, stare at that for a moment. Is that true? Remember I said the ultimate test? If I cover up the word limit, is it still true? So if I cover up the word limit, look at my numerator. This plus this minus this sum, is that still this minus this plus this minus this? Yes. I have a big quotient over delta x. Can I split it up into two quotients, each over delta x? Yes. I didn't do anything tricky with the algebra. Okay, now what? We're done. Why are we done? What is this? Isn't that the definition of f prime of x? That's the definition of the derivative applied to f of x. Oh, by the way, while we're at it, what is this? Right, crowd goes wild, confetti everywhere, dancing in the streets. That's it, we're done. We just proved the derivative of the sum is the sum of the derivatives. Is that big? That's astronomical. That is absolutely huge. As we say at my house, it's huge with a capital U. Okay? I would like to take the derivative of x cubed plus x to the 10th. What? So do I got to go through the whole limit process and break it up and do the delta? Or can I just take the derivative of this, which is what? 3x squared, plus the derivative of this, which is?
An x to the 9.
I'm voting that route. I don't know about you guys, but I'd rather go that way, because that is the answer. And wouldn't we rather get it without doing a whole lot of work? We just derived a formula that addresses both of these. The derivative of x to a positive integer power is just n x to the n minus 1. But I asked you a sum, which isn't that, but we just proved the derivative of a sum is the sum of the derivatives. Now, scalar multiples, that's the other thing we need to do. Because scalar multiples and sums are the most common thing we do. Okay, what if I want to take the derivative of k times f of x, where k is any real number? Now, if I asked you for the limit We know that the limit of a scalar times a function is a scalar times the limit. We know that. That's one of the most important limit properties. What do you hope the answer is here? Over there, the derivative of the sum ended up being the sum of the derivatives. What do you hoping this one ends up being?
K times F prime.
Yeah, we're hoping it's k times f prime. I can't just tell you it is, because in mathematics in general, these kind of things don't always work. I have to derive them. You see, the derivative of the product of those two functions is not the product of the derivatives. The derivative of the quotient of those two is not the quotient of the derivatives. Those things don't apply all the way across the board, but the sums and the scalar multiples from the limit properties we're going to see actually do. So let's do this. This is the limit as delta x goes to 0 of. Well, I'll write the first part. See, you can never miss this part. Right? Something minus my function over delta x. What goes here? My function evaluated at x plus delta x. So this would be k f of x plus delta x. This is a limit. Can I factor the k out? True or false?
Yep.
Okay, now what?
That's
We're
just-
done. That's f prime of x, isn't it? Oh my gosh. Is it really that simple? Yeah, it was actually that simple to prove. Okay, I would like to take the derivative of, okay, let's go a little bit crazy here. I want to take the derivative of 3x to the fourth minus 6x cubed plus 5x minus 7. Oh my gosh. Please do not rewrite this by physically writing four derivatives. It is absolutely correct to do the following. It is absolutely correct to say, and this equals the derivative of 3x to the fourth minus the derivative of 6x cubed and so on. And then to rewrite this as 3 times the derivative of x to the fourth minus 6 times the derivative of x cubed. This is absolutely correct. Don't do this. This is too easy. The derivative of a sum is the sum of the derivatives. The derivative of a scalar multiple is the scalar multiples of the derivatives. So just take the derivative one term at a time. This is correct. This is what you're doing, but don't rewrite it. It takes way too long. All right. So think of it like this. Four times
12x cubed.
3 times x to the
12x
third. Exactly. Everybody got that? The 4 comes out in front as a coefficient, but I already had a 3, so they get multiplied. All right, next. Minus
18x squared.
18x squared. Next.
5.
5, is it 5?
Yeah.
Well, it technically would be 5x to the
0.
0, so it's just 5.
And nothing.
So,
Because there's no x.
nada.
Ooh, that presents a dilemma. How do you take the derivative of a constant?
0.
Is it -7 or is it 0?
0.
It's 0. Can anybody give me a really simple reason? Keep it as simple as possible.
Because it doesn't have a slope, it's just a flat.
Well, no, it has a slope, but the slope is
0.
if I thought of the graph of y equals -7, that's a horizontal line, isn't it? And the slope of a horizontal line is 0.
Yeah.
The derivative of a constant is 0. Strangely enough, of all of the things in the first part of this course people struggle with, it's that one. The derivative of a constant is your favorite calculus question you could ever be asked, because the answer will always be 0. But sometimes we put the constant itself. We get confused. No, so this is it. Was this hard to do? Or would you say this was pretty simple? Yeah, this was pretty simple. You're liking this. This part of calculus everybody loves because it was really easy. But all I've shown you is positive integer exponents. We need to get to the point where we can say for any real number exponent, which by the way, we can't do for a little while, but we can do certain other things. So what I'd like to prove next, this is a biggie. I would like to do the following. For again, n is an element of z plus I want to take the derivative this time of, oops, okay. So in other words, I want to take the derivative of 1 over x squared, 1 over x to the 5th, or 1 over x to the 10th. Wouldn't that be the same as, by the way, is this exactly the same thing? Is it exactly the same thing as that? N is a positive integer. So I want you to take the derivative of x to a negative power. Agreed? Problem is I cannot use the limit on this one, not with the negative exponent. I have to use the limit on this one. And this one is, it's kind of big. You're going to like this because it's actually less work than the other one, because I already have the other results. Whenever we come up with results, okay, we just did it a moment ago. Whenever we come up with results, if I can get the result in the middle of my problem with those limits of the trig limits, if I can get the limit involving the sine x over x right in the middle of the problem, I can use that and evaluate it. I don't have to keep going. When we did these limits just now, if I could get this as a standalone statement, I don't have to do anything else. So we did some limit stuff a little while ago with x to the positive power. Maybe that will show up. So let's start this. This is the limit as delta x goes to 0 of 1 over x plus delta x to the nth minus 1 over x to the nth all over delta x. We okay with that? The first one is f of x plus delta x minus f of x. That doesn't look happy, does it? That's kind of icky. Wow. Okay, I need one quotient. Now, most of the time when it comes to algebra, calculus students are pretty good with their algebra, but not always efficient. I would like the next step to be these combined and simplified and everything all at one time. I don't want to do this in stages. I don't want to do the numerator as one stage and then make it one big blah, 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 blah. Just too much work. So I'm going to ask you a question. I have 1 over a minus 1 over b all over c. I'd like to make this into one quotient, but I'd like to do it one step if possible. Now, first rule of thumb is you cannot have a quotient in a quotient if your answer is finished. Do you agree? None of us, the final answer to the question was 3/4 over 5/7. That's my final answer. Do we all agree that that's not finished? Even if it were correct? We'd say, no, I got to make this a little bit cleaner than that. This is not finished because I have two quotients in the numerator. But a lot of times we don't realize that things can be simplified much easier. I mentioned this on day one, and I'll show you right now. Most algebraic processes we ever learned in our life were really quite inefficient. They weren't wrong, they were inefficient. And particularly when it comes to manipulating quotients and simplifying quotients, there's so much math we're going to do this semester where if you're not efficient, you can take a problem that isn't necessarily long, and it'll be really, really long, and we can get lost really quickly. Now let me remind you of stuff you already knew as quotients. Let me write it this way. What if I had a over b divided by c? I'm going to write the old-fashioned way. A divided by b over c. A over b divided by c over d. Do you agree these are the only three ways I could have quotients within a quotient? I'm keeping it simple. So obviously the first one is the same as saying a over b over c. The second one's the same as saying a over b over c. And the third one's the same as saying a over b over c over d. You're doing the big bar. And most of us do the right thing, but most of us take a lot of steps. We take a lot of steps to get there, and then in the end, we're still not sure if we did it right. Okay? But everybody knows whenever you're dividing by a fraction, you always, multiply by the reciprocal and then do all that stuff. That's all correct. Is it the fastest and easiest way? No. It's the longest way. I'm going to show you how to do each of these in exactly one step. You're not skipping a step. You're not doing any steps in your head. You're doing the only step that's necessary, the one you weren't shown. The only problem with any of these is where there's a quotient. There's a quotient here. C is a whole thing. Think of C as an integer. C is not a quotient. A over B is a quotient. What's the only denominator then within any of the quotients? The B. What's the only denominator within any of the quotients? C? I have two denominators within these quotients. I have a B and a D. This is how you should have learned this. One step each. And there's no possibility I could do the wrong thing. By the way, even calculus students are going to miss this one half the time because they're going to flip the wrong one over or do weird, goofy stuff. You see what I did? I didn't flip it over and multiply. Why? That takes a whole nother step, and sometimes we mess that step up. No, you multiply by the common denominator. In this case, BD. In this case, it was only C. In this case, it was only B. In this case, I'm going to do this by just going like this. And the next thing I write is the final answer. The next thing I write. Because what's 1 over A times AB? B. What's 1 over B times AB? A. What's my denominator? I'm not skipping any steps. I'm not doing any steps in my head. I'm showing you that because this looks really complicated. I would like to do one step and be completely done with that quotient. Are you guys okay with that? And I don't mean a step in my head. I mean the only step necessary. I have two quotients in my numerator. Generally speaking, unless A and B have a common factor, then the common multiple is just simply AB, correct? These two cannot have a common factor because I'm adding something within here. So I'm going to multiply top and bottom by this. Now, I'm physically writing it out. When I'm doing it, I will do that step in my head because I know what that step is. When I'm doing it for you, I'm going to write it out. But the next thing I write is the completely simplified version. Key is, what's my denominator? It's a big, ugly looking bunch of stuff. But what's my numerator? X to the n minus x plus delta x to the n. Did everybody follow that? By the way, there's no more simplification necessary for the numerator. I now have exactly one quotient. I don't have quotients of quotients. Most of us have been trained to take time to make that into one quotient, then do the C, then multiply by 1 over C, which is now about 4 steps. And then we pray that we got the answer right in the end. And I'm saying, no, that's one step problem. Do it in one step and it's easier. We did this in one step. Now, my numerator looks backwards, doesn't it? It looks backwards. I'd really rather the subtraction go the other way around. Do you agree? Well, would you rather the subtraction went the other way around? Because then it would look more like the definition of the derivative. Can I factor out a -1 from the top? Is that legal? Can I do that? Or I'll put a -1, it makes it easier. Can I do that? Is that legal? The limit of a constant times a function is the constant times the limit? Yeah, I can factor the -1 out. But let's go a step further. Isn't the limit of a product the product of the limits? Oops, sorry. True or false? Remember, if I cover up the word limit, are they still equal? If I cover up the word limit, then this thing here is equal to this thing here. If I cover up the word limit, well, let's see, -1 times my numerator, okay, same numerator, and this denominator, yeah. Do you all see it? If I cover up the word limit, algebraically, I have the exact same thing. And I'm done. I'm done. I can now evaluate both of these limits. Wait a minute. How could I possibly evaluate both of these limits? Well, what is this limit? Didn't we just do this right before the break? Isn't that n x to the n minus 1?
Mm-hmm.
We just did this before the break using the binomial formula. That is that. Agreed? We got another dime. Question is, what the heck is this? This is kind of weird. What's this one? Oh, wait a minute. Delta x is going to 0, not x. Nothing's. Can I evaluate this? Yeah. If delta x is going to 0, then this term's just becoming x to the n, isn't it? I have x to the n, x to the n. Delta x is going to 0. I can evaluate this guy. There's nothing weird happening here. So what have we got so far? This would be just 1 over x to the n times x to the n. So are you telling me that when all is said and done, the derivative of this, it sure looks like we're saying the derivative of 1 over x to the n, which is, by the way, the same thing as saying the derivative of x to the negative n. I'm going to write it like that for a moment. We know that's true. We haven't done anything yet. I'm claiming that this is the answer. Well, let's see. That would be negative n x to the n minus 1 over x to the n x to the n. Can we clean that up a bit? Okay. Pull the negative n out. I have x to the n minus 1. Can I write that as x to the 2n? Would that be easier if I wrote it like that? Rules of exponents? What's the rule here? What do I do with these exponents?
Subtract.
Subtract them. So shouldn't this be x to the n minus 1 minus 2n? That's kind of ugly, isn't it? And what's that? That's x to the negative n minus 1. You're going to like this. What have we just derived? Bring the exponent down, decrease it by 1. Isn't that the exact same rule we just did for a positive exponent? Is it exactly the same thing? Yes. Is that a good thing? Oh, yeah. That means I can take the derivative of negative exponents exactly the same way as I did positive exponents. I bring the exponent down and I decrease it by 1. Not because I told you, we just did it. So I want to take the derivative, let's just say, of, I don't know, 4 over x to the 5th power. I can't take it in this form. That's the trick. What do I have to do first? Write it how?
4 times x minus to minus 5.
Yeah. I write it in this form. Now what do? Bring that down, and what do I get?
Negative 20.
Negative 20x to the
Negative 4.
6.
negative 6. Now, I am done with the calculus. I'm completely done with the calculus. Do we consider this a finished answer in general? Why not? Yeah, I have a negative exponent. I started with this and I changed it to this for the purposes of being able to use the calculus much easier, and now I did it, but it is good form to now change it back to a positive exponent. We consider, generally speaking, a negative exponent not to be simplified. It's not incorrect. Would you leave a final answer 8 divided by 4? You did everything right, your final answer is 8 divided by 4. Would you leave that as a final answer? No, because you can simplify it. You can go a step further. If my final answer is x to the negative 6, I can go a step further. So we consider the last one to be a better answer. You like this rule? You should like this rule. So x to any integer, positive or negative, I bring the exponent down, decrease it by 1.
So the fraction would be like negative 4 over x to the 5th, and it would just be positive 20x to the 6th.
I'm sorry, you said negative 4.
So yeah, if it was negative 4
Oh,
over
if
x,
that 4 was negative?
then it would be positive 20.
Yeah, if that 4 were negative, then yeah, because it would be a different coefficient. Yeah, isn't that nice? Now, here I'm going to ask a little faith. I don't like doing this in math. Over the next several weeks, we're going to be able to do more. We're going to go way beyond this. I'm going to prove to you, I am going to prove absolutely to you, sorry, I can't write today. No, I can't write any day. I'm going to prove this is true. Well, Mr. Brown, you've already proved this is true. No, I only prove this is true for positive and negative integers. What if I have fractional exponents? What if my exponent is square root of 2? I'm going to prove to you that this is actually true for all real numbers. Do you like that idea? You should. That's cool. I can't yet. There are tools that we haven't learned yet. In fact, I'm going to go out on a limb here. On the 18th, I can formally prove that that is true for all rational numbers, fractions. On the 18th of September, I can prove that because we'll have the tools. And on, sorry, I'll find it in here. On the 25th, I'll be able to prove it's true for all real numbers because then we'll have logarithms and things. I'm going to prove that's true always over the next few weeks. But I lack the tools today because there's a few things we haven't learned. So I'm going to ask you to accept something. I'm going to ask you right now to accept that this is true always, knowing I'm going to finish proving it later. Does anyone have a problem with that? Please shake your head. Say, no, I don't have a problem with that. Did you have any problem, the area of a circle is pi r squared? No, but you're not going to be able to show that until Calc 2. Just telling you. Today in Calc 3, we derived the circumference of a circle was 2 pi r. It took Calc 3. Nobody had a problem accepting that as kids, but you can't prove it until you get to calculus and beyond. A lot of them are even Calc 3s. I'm going to prove it's true for every situation. We just can't do it yet because there's some more tools. But I want you to be able to use that fact as we go. I want you to have that in your tool belt now because you can answer more questions that way. So, I'm going to do an example of something. This is one that actually comes up a lot. The next one. We're going to do some evil problems. Sometimes the evil ones are fun. Now, I'm not going to use the formula. I'm going to do this using limits because I'm going to show you how to do things in general using limits. And you're going to get faster. One of the things we do is we use the limits to get all of our derivative formulas. And once we have them established, we don't need to use the limits. The limits are a stepping stone. But then we're going to use the limits to do, when we do the second half of the class, we do the dark side of calculus in the second half class. See, everything we do now, we work with derivatives and things. Do you guys know what we do in the second half? We do the anti-derivatives. So I call it the dark side of calculus. You go from Jedi to Sith at that point. And it turns out that's the higher level of reasoning. But everything we do, we are able to do it in reverse. And everything we do involves limits. Then we get the second semester. And everything we do when we set up involves limits. Then we get to Calc 3 and everything we do involves limits. You don't stop doing limits till about, a month left in Calc 3. They constantly come up as the vehicle we need to get to the next thing. But they are a building block. They're a stepping stone. Once we establish this, you won't need to do the limit to do this derivative again. But you don't know how to do a sine or a cosine or an e to the x or a log x. Those all involve limits. And then once we build them, we'll have those facts. So I want to do this using the limit because it's a good exercise in manipulation right now. So this would look like x plus delta x minus the square root of x all over delta x. And I don't think I can factor and cancel this. Darn. Wait.
I mean, you put to the power of half.
Yeah, it won't help any though. Conjugate. Good. What's the problem child? The problem child is the delta x. But the delta x on top lives inside the square root. I need it not to be in the square root, and the only way I can do that is to conjugate. So what do I want to multiply top and bottom by exactly? Anybody?
Square root of x plus delta x plus the square root of x.
Perfect. And that is a totally legal move, and there's no way that's ever zero and all that kind of good stuff. If I do that, then my numerator is going to be way, way, way simpler. And I will probably be able to easily navigate to the end. Now, we did a problem not that dissimilar to this, I believe, on the first quiz, didn't we? You guys you did something with the square root. Because right now, the problem child is the delta x because that's the thing that's causing my denominator to go to 0. So I really need to be able to cancel with the delta x that's on top. I can't because it's inside a root. But by conjugating, remember, a plus b times a minus b is a squared minus b squared, and then that gets rid of all my roots. So what is my new and improved numerator? It's just x plus delta x
minus x.
minus x. Do you all agree? It's root squared minus the other root squared. My denominator is a whole bunch of stuff. Don't distribute. I don't want to distribute. Because on top, those x's cancel, and I now have just a delta x. But on the bottom, I also have a delta x. Can I simply cancel the delta x's? I can't evaluate yet because right now numerator and denominator are both tending to 0, but when I cancel the delta x's, neither one of them will be going to 0. Now I have a 1 on top. I have an x plus delta x under the root plus an x. Stare at that for a moment. Is that an indeterminate form? Well, the top's a 1, so you say no. Is my denominator going to 0? Is that an asymptotic form? No, delta x is going to 0, which means I'm just getting what? Root x plus root x on the bottom. Do you agree? Can I evaluate this limit right now?
Yes.
Yes. You're always looking to evaluate your limit. At the very first opportunity you want to do it. We could not do it any step before this. Still an indeterminate form, way too busy, ugly as heck. I can evaluate this, and what's my answer going to be? 1 over 2 root x. Which, by the way, you're going to remember over time because differentiating the square root function is actually a fairly common thing in calculus and physics. It comes up a lot. I don't want anybody here to memorize the result. No, you're going to have formula sheets. You're going to get to bring those to the test. I don't want anybody to memorize. I want you to learn through repetition. You cannot memorize math. You memorize definitions. You can't memorize strategies and results. Okay? Does anybody here ever watch sports? Yeah. Anybody watch tennis? I wanted to watch the US Open, but they removed it. So, you know, you're a tennis player. You're a professional tennis player. You are Roger Federer, okay, and I'm Novak Djokovic. So I hit the ball to you, and you've memorized every possible way I can hit it to you. So depending on how I hit it to you, you've memorized your return. Is that how it works in tennis? You'd be standing there 5 minutes after I hit the ball. Okay, so now I see which it's return 107. No, you react. You can't memorize. You're driving a car. You've memorized every conceivable situation on the road. No, you react. When a person cuts you off, you react. You don't memorize. If you're playing sports, there's all reaction. There's no memorization. When you're doing math, I'm going to memorize every possible result to a math question. No, look at the one you're asked and react to that, and literally. So you have to know what the right formula is and how to execute it, but you don't have to memorize formulas. All calculus formulas you will learn over time through repetition. That's it. You just do them enough times, you remember them. And you're going to get to write down the calculus formulas for your test. No, don't memorize. Know how to use them and know which ones to use. This is a common result. People remember this just because it's so common. Now, we just derived this using the limit. You got to admit, that was kind of a beautiful thing. Now, do we have a shortcut that we just employed? Yes. Can I do this? If I do this and I use the exponent, then what is my answer? Remember, this symbol in front says take the derivative of the thing that follows. And once I do that, I don't write the derivative symbol again because I've taken the derivative. So what follows this? 1/2 x to the
-1.
-1/2, which is the same as 1 over 2 root x. Oh, yeah. That's a good thing, isn't it? It's more of a... A common error I showed at the beginning of class is when we take a limit and then we write our answer as the limit of the limit. That's incorrect because that means I'm not done. When I teach remedial algebra, one of my favorite errors, this is my absolute favorite error. When people learn square roots, let's face it, square roots are fun to take. So I'm teaching a remedial algebra class and I say, what's the square root of 16? Well, that's the square root of 4, which is the square root of 2. What do you think? Because taking square roots is so much fun, we just want to keep going, don't we? Are any of these statements true? No, because the square root of 16 is 4, I'm done. The square root of 4 is 2, I would have been done. I just kept writing square root. When you're doing this process, some people inadvertently write the derivative again. Oh, that means I'm still going. When we do a limit, sometimes we inadvertently write the limit again, which means I'm still going. No, once you evaluate, you're done. Once you take the derivative, you're done. There's nothing else to do. So, you know, this no work. Question so far? Okay, let's do another one. Let's do one that actually the formula won't help us for. We don't have a formula for this one yet. This involves something we're going to learn next week called the chain rule. But we haven't learned it yet. Therefore, the formula we just did with the exponents won't work on this one because of the +2 part. It would only work on this. So let's do this as a limit problem again. Again, it's good exercise in manipulation because we're going to be doing limits for quite a while. And I want it to be to the point where you don't question your algebra. Whether the algebra is easy or hard is not relevant. It's, am I going to do the correct move? I don't care how long it takes. Am I going to do the right move? Because if I don't, then the next thing I write might not be correct. So this will be the limit as delta x goes to 0 of. All right, I'll do my part. Okay, do you all agree with that so far?
Mhm.
That's the part you can't get wrong. Function delta x. What goes first?
1 over x plus delta x plus 2.
Good. I'm replacing x with x plus delta x. Now, I don't know what the answer is supposed to look like, but I know that's correct. Right now, this is an indeterminate form. How do I know? Because if I replace delta x with 0, then my numerator is 0 and my denominator is 0. I know that. Delta x is the problem child. I need to rewrite this in such a way that the delta x's will eventually cancel. Right now, they're not going to cancel because of where it lives. Conjugating won't help. But remember what we did a moment ago when we multiplied top and bottom by the common denominator? That's the only thing that'll work here. What is the common denominator? Well, I have two different denominators, so how about x plus delta x plus 2 times x plus 2? Now, when you do enough of these problems, you could write the next result without physically writing this because you already see what to do. I don't have a problem with that. You know, with you getting the next thing correct because a step was really obvious in your head. But when you're writing up a solution, let's say you're at work and you're doing a project and other people are involved, should you ever skip steps? What do you think? Yeah, because the people reading it might not be able to follow your reasoning and they might not see where your result came from. So it's safer to say, I'm going to explain to you everything of the way. See, I'm watching the movie and I'm pretty sure what I know what's going to be happening next, so they can just skip that part of the movie and fast forward 20 minutes. Or maybe not a good idea. We don't do that when we watch movies, right? They don't skip sections because it's really obvious what's going to happen. No, so you really want to have every step follow from the step before. You just don't want redundant waste of time things. So the next thing I'm going to write is going to be something like this. And what's on top? When I distribute on top, I'm going to get x plus 2 minus x plus delta x plus 2, which is a beautiful thing because almost everything cancels. What will be left on top? Only delta x. Is that a good thing? Yeah, because that means I'll be able to cancel it. I can't cancel it yet because I still have a bunch of stuff going on top. Don't start canceling. You can't do that. I have people all the time. I'm going to cancel in the sum and difference and cancel in the quotient simultaneously. Mathematically, that's absolutely impossible, by the way. It's not possible to cancel a sum and a quotient simultaneously. They're different orders of operations. And when people do that, don't write this down. I see people do this one all the time. I see calculus people do this one all the time. X minus 1 over x is 0. Because I started by canceling the x's, and now it's 1 minus 1, which is 0. Is there anything that I did that was correct in this problem? No. This is as awful can be. If you look up awful in a dictionary, it'll probably be this. But calculus people do this all the time because they want to combine steps that cannot be combined. You can't combine an addition and multiplication. In algebra, I have an addition and I have a multiplication. I have to do them separately. There's an order of operations that cannot be done simultaneously. So here, can I mentally distribute the negative on top? And the reason I want to do that, I'm lazy. I don't want to write the top twice. Or, if you're not sure, you really go like this. Can I go like that? I just don't want to lose my negative sign. Everything cancels except the delta x, except the delta x that I'm going to be left with is negative. That's key. I'm a big fan of doing stuff like this, writing over the top. It's scratch work. But then I know exactly where everything came from. Now can I cancel it? Oh, yes. So my numerator now looks like it's going to be a -1, and my denominator is going to be this product. But this product is very safe because only delta x is going to 0. As delta x goes to 0, and by the way, I like it when people do stuff like this. Does delta x equal 0? No, delta x is approaching 0. But I'm giving myself a mental hint, okay, what's taking place now? I have this whole thing and the delta x is going to 0, meaning this term's approaching just x plus 2 times x plus 2 with a -1 on top. Can I now give the final answer to the question? At this point, can I give it? Yes. I could not have done it a step before, but I can now. So what is the answer? It's -1 over the square of x plus 2. Okay, and for the amount that we know now, this is the only way to answer this question. I'm going to show you a shortcut later, but we don't have that shortcut yet. We won't have that crazy shortcut until a week from today. I look at the schedule. So a week from today, we'll learn a shortcut. But there's a whole bunch of in-betweens. Hate to do that, but you can't learn all of calculus in the same day. We do this in baby steps. Okay, any questions so far? It's kind of cool, the stuff you can do now. Yeah, Cece.
So, does that mean that limits in a way are derivative?
I'm sorry, say again?
Are limits a form of derivative?
No, but a derivative is a form of a limit. The derivative is a form of the limit. If I do this limit, that's the derivative. But just in general, on the first quiz, when you were doing limits, there were no derivatives. You just said, I have this, so I was looking for things like holes, removable discontinuities and things. No derivative. Think of it more like, I have a graph with holes and I was trying to identify the hole a lot of times. In the next stuff, I have graphs maybe with vertical or horizontal asymptotes. I'm trying to learn where they are. That's what some of those limits. The limits to infinity, I'm trying to identify horizontal asymptotes. The limits to where the denominator is 0 and the numerator is not, I'm trying to identify vertical asymptotes. So there's no derivatives in those, but I start putting them all together. So we use the limit to define the derivative, but the next thing we do, we don't necessarily need limits, because I've just established a really powerful formula a moment ago. So here's what I'd like you to, so I'll try this one. I want to do the derivative of, how about 6 over x cubed minus 4 over the cube root of x? Oh my gosh. Can you answer this question? Is it even possible? Do we have the tools? Yes or no?
Yes.
Yes. Can you answer this question as stated? I'll give you a hint. I'm pretty good at this stuff, and I can't do that yet. So what are we going to do first?
Split it.
Separate.
Not split it.
Or do each individual.
No, that's the same thing she said.
Sorry, I just have one question. Is that in parentheses or brackets? Because earlier you drew one that looked like a bracket, and I've been really lost. So I don't want to draw brackets on a quiz.
Brackets and parentheses mean the same thing. It depends. If you already have parentheses, it usually is it. Here's why. All right, I've got. You're using your graphing calculator, and every time you do anything in parentheses, you get an error. Why? because you don't have the same number open as you do closed. So when we write things, what do? We tend to try to alternate them so we can tell which one goes with which. Parentheses and brackets mean exactly the same thing. It depends. I choose to do them differently because if I have a whole lot of stuff, sometimes parentheses are harder to read. Sometimes I like to bracket it. It's easier to read. In this case here, it wouldn't have made any difference. But if I have more than one thing going on, and there's parentheses, they're called embedded parentheses. I don't like parentheses. That's what your calculator will show. I like alternating because I'm far more likely to make the correct interpretation. See, I see this one closes this one. Does everybody understand? So the question is, is there a priority? No, it's readability. It's readability.
For the differential, would we have to change the x's to,
So when I said, can we do it as stated, the answer is an overwhelming no. There's no formula for either one of those. I have to write them as exponents, then I can do it. See, the formula is differentiating x to the nth power. Neither one of these are in that form. A root isn't an x to the nth power yet. So my first thing I'm going to do, and this is never hard, but I got to get this one right. This is 6 times x to what power?
-3.
The -3. We all agree that's -3. Minus 4 times x to what power?
negative a third?
-1/3. Now, for a lot of us, roots and fractional exponents aren't as comfortable as they can be. Remember, cube root is 1/3 power, square root is 1/2 power, and so on. In the denominator, it just becomes a negative exponent. If I get to this stage, should the derivative be easy or hard?
Easy.
You notice I didn't give it in between. It's got to be easy. Because now it's not even calculus, it's really arithmetic. I'm bringing the -3 down. It's multiplying by the 6, leaving me what?
-18.
-18. Now
X to
here's
-4.
where we get into trouble. We sometimes go the wrong direction. You have to subtract 1 from that exponent, which means
-4.
1 is -4.
Minus
Tell me the only error. -2. It's -4 because I'm subtracting. What's this one?
positive 4/3.
Plus 4/3 x to the,
Negative 4/3.
good. Now, both of those are going to go back in the denominator. Now I have a choice. Oh, I don't need pencils, sorry. Negative, by the way, a common error, and it's a really silly error, 18 doesn't go in the denominator. X to the -4, x goes in the denominator. 18 is the coefficient. Coefficient can't go in the denominator, and that doesn't make any sense. But we sometimes make that mistake. Plus, now I have 2 choices here. It's 4/3 x to the 4/3, or it's 4/3 times the cube root of x to the 4th. Both are absolutely correct. The original problem used roots, that's true. Which answer is easier to work with? The root or the fractional exponent?
Fraction.
Fractional exponent. No, this is easier to work with. You had to change this to a fractional exponent in order to do the math on it. Does a fractional exponent and a root, is one of them considered a higher order, or is one of them considered better, more simplified? We can go on and on. X to the 1/2 square root of x. Is one better than the other? No, exactly the same. The difference is, most of us, the answer is square root of x. What's the square root of x? I have a really simple rule of thumb. If the answer's of the form x to the 1/a, that's the same as the 8th root of x. That's the same thing. If it's x to the b/a, then the answer is the 8th root of x to the b. I never do this one, ever. And I'll usually do this one. Cube root x, 4th root x, 5th. Easy. The moment I put that other thing on, never. There is no advantage in any conceivable situation. You don't even have a key on your calculator that will let you do this one. Well, most of us will get it wrong most of the time. We'll switch it. We'll do all sorts of crazy, wild, goofy math. When all said and done, you know, complete chaos. No, if you have a fractional exponent like 4/3, leave it as 4/3. Easier to work with. The problem comes a lot of times when I convert back, I make a mistake converting it back because it's less familiar. So fractional exponent is always acceptable. The only thing we said we're gonna consider not quite done was the negative exponent. That's the only thing we gotta deal with. I can leave the 4/3. Totally. Now, when something is a square root, I usually leave the root because it's easy to recognize, easy to work with. But if it was the square root of stuff raised to a power, I'm gonna use a fractional exponent every time. That's hard to work with. It's more difficult to translate and stuff. But again, that's a personal choice. And I say this in all seriousness. A lot of times it's not about being right or wrong. It's what's the most useful form of your answer. Because in reality, and it's hard to understand at this level of math, but by the time you get to Calc 3, they start understanding this, they've had physics. You're doing this really gnarly calculus problem. That is the beginning and the ending of everything. You're all done. That's all there was. Or is it maybe just one step out of 10 of an actual problem? Yeah, that's probably more accurate. You're doing the calculus. I'm pretty sure, I could be wrong, but I'm pretty sure none of you is going to have that job where they hand you a sheet of paper with a bunch of calculus problems, you solve them, you turn them in, you get paid. By the way, when you find that job, please tell me I want that job. No, you have situations, you have to model them, figure out what is the math and the physics and the chemistry and the engineering and the biology and the computer science. And the calculus is one step in the problem. And now the result of the calculus answer you're now going to use for the physics and on and on and on and on. Every time you ever do a calculus problem in real life, it's just one small part of a bunch of bigger stuff. It's never the beginning and ending of anything, ever. Sorry to disappoint you. That's why you have to have all the other classes. So when you're doing the calculus problem, I'm saying the form of your answer, if I have to use this answer now for the next step, what form of that answer translates the best to the next step? Or I'm handing it to you to finish the problem. Which version do I want to hand you? Everything correct is acceptable, but what version is going to be the most useful and easy to use? So that's what you partly want to train yourself in. The moment you guys have physics, some of that will be clearer. Because you'll say, oh, in physics, yeah, when we have problems like this, it's so much easier to work with numbers that are expressed this way. Like fractional exponents are so much easier to work with because I have a key on my calculator that I can do a fractional exponent. But I don't have multiple root keys on my calculator. I only have square and cube root. And when things are raised to powers, it's even messier. Does that make sense? So it's not about right or wrong, it's just about useful. If you're right, you're right. I don't care what version you give me. But there are versions that you'll find are more useful down the road. I think I would always go with something that looks like this. Just because I know in the next step, that person's gonna have an easier time using this. Okay? All right, guys.